Welcome everybody, and thank you for joining today's ANGA COM Online Special session, FTTX and DOCSIS. We have today a great set of panelists, good friends from the fiber optic industry and good friends from the cable industry. The ANGA COM and I myself, we are very proud that we have Mike Thornton from SCTE today with us as a co-moderator. Maybe Mike, you can say some words?
Thank you, Carsten. Yes, welcome everybody. This is quite a privilege for me to be here, and I thank Carsten for giving it to me. The SCTE is proud to support ANGA COM. We've supported the exhibition for many years, and today we have an excellent set of presentations for you on the online special fiber to the X and DOCSIS sessions, in which case I shall hand you back to Carsten.
Oh, thank you, Mike. That was great for your good words. Appreciate. Well, ANGA COM is proud of the cooperation with SCTE, the Society for Broadband Professionals, and well, today's ANGA COM Online Special FTTX and DOCSIS is a starting point of a new series in our ANGA COM portfolio. We plan in the next months several online specials for different topics, like for topics in strategy topics and in technical topics. And if we have many audience right now here, if you like to become a panelist or become a speaker here in such an ANGA COM online special, please come back to us with the email address you already have. Well, please give me a chance of a short warm-up of our today's session. Today we have two panels. After each panel, we like to have time for urgent questions, and for the audience, please type your questions into our tool, and we will read your questions and bring it to the screen at the end. After the last Q&A, after the second panel, we will start our general discussion. There we will select the incoming questions, and at the end, that is the highlight, at the end, you have the chance to ask oral questions by raising your hand. Yeah, you see it on your dashboard, and there you can raise your hand. Well, we like to train a little bit this ongoing process with the first poll we prepared, and at the end of the discussion here, we will come up with the result. Please mark the right selection here for this question. And during the next time, we will jump into the first panel. Well, let's get the start to dive in. We start the first panel, fiber optic infrastructures on the way to a success, with Dave. And we are really happy to have Dave from CommScope with us. He's a regional vice president, solutions and architectures, and he is very well known in the business, and he is a good friend, and he has a task to kick off our online special. Well, Dave, the floor is yours.
Thank you, Carsten, and thanks for the introduction. Let me just set the environment. Here we go. So thanks very much for giving me the opportunity to present today. I'd like to kind of just give a quick overview in the 15 minutes of how we see the trajectory and the path of direction for how access architecture, specifically around PON, will look like in the near term and future evolution. Just to kind of cover, and I'm assuming we have quite a wide range of audiences here from all various backgrounds, including cable and PTT and more FTTH. So just wanted to kind of start off by just explaining some of the current cable operator technology and the consumption of PON technology. It's probably not a well-known fact that some operators around the world have been consuming PON technology for many years, if not decades. And for some of you that I'd like that have been in the cable industry for some while, will understand what DPoE is, or the DOCSIS provisioning of EPON. And I'll just cover some of the background of that, because it does actually give some familiarity in terms of how we start comparing PON architectures between both the telco based, which is ITU-T based, and the cable based, most predominantly IEEE. And then I'd like to then just drill down into the seismic shift that we'll soon start to see in terms of how we disaggregate from single box, single system technology for cable PON into a disaggregated environment. And I'll take exactly the same approach with the telco architectures. And following on from that, I hope you will walk away with some of the conclusions around that there's a lot of similarity in terms of where the convergence is in path of directions from an architecture perspective moving forward. So with that, as I mentioned earlier, the cable operators have used and consumed PON technology across the world for some time now. Not to be too verbatim around it, but if you look at the market categories ranging from the US, large, mid-sized, smalls, across the Canadians, the Latin America regions, European MSOs, and Asia Pac, you can see how they predominantly, or what their consumption of the PON technology has been. And without going through it line by line, you would see that 10 gig EPON leveraging DPoE as a natural progression for large cable operators in the US seems to be a frictionless approach. However, some of the mid-size have opted for ITU-based, initially kicking off with GPON and moving towards 10 gig symmetrical PON technologies. And there is a spectrum of different adoption models across different theaters, and again across different market segments ranging from residential to backhaul type services, MDU services to backhaul type services. So you can see where these consumptions had been used. For the folks that are not from a cable perspective, what is DPoE? It is DOCSIS provisioning of EPON. There were some multiple objectives, but the objectives that wanted to be covered by Cable Labs is that we wanted the MSOs to leverage as much as possible of their back office systems to be used for PON. It was critical that as they started on this journey, that there wasn't the forklift requirements, very mature DOCSIS back offices in terms of managing the DOCSIS environment from provisioning through to service enablement, i.e. configuring the DOCSIS.cm files, network management, SNMP, etc., and understanding of alarm enablement, and also collectors and secure login. So one objective was to leverage that and reuse that. There was also work undertaken to define the management interface between the back office and the ONU. This has become DPoE AM, or as part of the mediation service. And then to facilitate vendor interoperability with the likes of Siphon. So operators had the benefit of some comfort factor between ONUs, ONTs, and the OLTs. This I lifted from a Cable Labs Expo, really just to kind of draw the comparison between what is referred to on the top, the CMTS view or cable view, and with the addition of an OLT leveraging DPoE. One key point here, the virtual CM actually acts as the mediation entity between the IP management and the EOAM, which is basically the communication with the ONT. But you can see that the DOCSIS OSS services are common across both architectures. There are some notable differences, and here is where the discussion gets quite interesting between the telco and MSO type architectures. In the telco space, it very much is a multi-box solution with different services running on each element of the architecture. From a GPON perspective, this does all the layer 2 and scheduling. This would be in the OLT. We would have a northbound switch fabric, basically either layer 2 just to connect multiple OLTs northbound. And then at a BNG level, this does all the control plane and downstream user plane and traffic management. So you can see that this is kind of like the stack that the telcos would deploy. Whereas in the cable architecture, we've taken, and what the industry was asking, we've taken the scheduling function that would be sitting typically in an OLT. We've incorporated some of the DPoE mediation, both mediation elements as well as the control plane, and then also providing full layer 3 backhaul as well as the OLT management plane. So the reason why DPoE was quite useful is that we could still incorporate this all into a single chassis. That became CCAP, and the telco model is on the left. Just drilling down a little bit more before we expand on some of the disaggregated elements. So we can take the CCAP, run potentially in a hybrid mode. You know, this was offered so operators, cable operators in this case, can migrate from a DOCSIS environment to a PON environment seamlessly on the same chassis, leverage some of the node splits, rather than doing node splits, leverage PON insertion to actually pull off, you know, do some subscriber shedding or so on and so forth. So this is the architecture from an EPON perspective, all controlled by the same back office that was running in the DOCSIS environment for many years previous to that. But I'd like to now explain where the path of direction is going in terms of the disaggregation. And we talk about aggregation to disaggregation really is an exploding of some of the software functions that would currently be, as mentioned before, housed in the same chassis. So here on the left, we have a depiction of an integrated CCAP acting as a DPoE OLT, providing 10 gig EPON. The first thing we do to disaggregate, we replicate what would be the switch fabric within the box. Now, this is achieved by a spine and a leaf type aggregation. So effectively, we're replicating what would be the backplane of an integrated device. We then start looking at how we start disaggregating elements of the control plane. Now, this could be either layer 2, layer 3, but certainly we could be looking at this as an SDN controller or a controller of such that would sit in a cloud-based infrastructure. And then maybe for layer 3, we could implement this element on either, it could be a PNF, it could be a physical network function, but typically when we talk about disaggregation, this will be on a NFV or a network function virtualization elements. And we start building out, we start withdrawing some of the software functions like the management plane and putting that into the cloud. So this becomes a virtual OLT management function that is there. And obviously from the mediation perspective, we start pulling off some of the DPoE functionality and virtualizing that. This leaves us with the physical connectivity or what the OLT would be. Now, this actually could be still residing in a node-based form factor or a potentially shelf or a shelf-based for central office type functionality. So here for cable DPoE, we've basically pulled out some of the functionality and actually put this up into a data center architecture. Expanding on that, and just a bit of a busy slide to address that, all the functions that we've taken out and we've co-hosted them, we call an OLT manager. This would also support obviously it supports the management function, the DPoE function, and possibly later some of the virtual DBA and CODBA. Key to point out here that the traffic management, the DPoE traffic management function down here is still where we do all the lawful intercept, all the downstream subscriber management, and basically usage collector for data records, etc. The top of this remains all the existing OSS configuration and provisioning, telemetry and accounting stays intact. As we look at a telco-based legacy architecture, as mentioned before, we split it across 3 separate devices from the OLT up to the BNG and the various software functionalities or functions that sit within that. If we take the same approach of how we disaggregate in the telco-based environment, we have 2 boxes effectively to disaggregate. I've omitted the switch just for clarity on the slide, but the switch fabric effectively becomes the leaf and spine switch, and with either data center interconnect or co-located. We split out the control plane functionality. Now this is the first time we start introducing a VBNG function. So we house the control plane functionality in an SDN layer. And then for upstream traffic management, we could also do that either on a physical network device, or we could start virtualizing those elements of the software construct into a data center architecture. The management plane is then transferred into an SDN environment, and you start seeing the similarities that we've had between both the DPoE environment as well as the ITU-T environment. And the interface, the OMCI, again, another virtualized position we can take here. And as I mentioned before, the OLT becomes the packet forwarder in terms of some of the remaining scheduling elements stay intact. We can start adding in cooperative DBA for some of the more preemptive type services for quality of services. Those can stay there. And then again, form factors around this, it could be either a node or a shelf-based environment. So you can see some similarities between how the converged architectures between both cable PON and ITU PON are looking moving forward. As we take a bit more of a software functional view, again, similarities again between the OLT and the OLT manager. The whole concept here is we use standards-based and open interfaces. The only comparison that I would draw is that, as with BDF in broadband form as well as in cable, between the OLT and the virtual OLT management function, there is some proprietary stuff there, but it can be also native NetConf moving forward. But that's a similarity between both BDF and IEEE. And then one point I'd like to draw attention to is where the disaggregated user plane sits. Here I'm showing this as an adjacent function that sits northbound of the S-leaf, but effectively we could pull that user plane functionality direct into the OLT at a later date. This will compress the architectures from a hardware perspective, but also give a more cohesive and almost single point of management functionality moving forward. And that user plane can include all the typical stuff, the routing control, data forwarding, all the necessary traffic management, lawful intercept, and obviously act as a collection point for user data records. So this was explaining the disaggregated PON architecture from an ITU perspective. It looks very similar to a Ethernet, a DPoE environment. And then just with a sort of conclusion as we finish off the first session, you know, the deployments of a virtual OLT management plane and ONU management have been adopted quite some time ago in the cable industry. I mean, by disaggregating the management plane, you know, we could have called that SDN even before the term was coined. CableLab's DPoE defined, as I mentioned before, the standard northbound interfaces, the interoperability between the OSS and the mediation system, and it really was conceptualized to provide full interoperability. I do find it interesting that as we disaggregate, there is a comparison to be drawn between both OLTs in an IEEE perspective and OLT disaggregation in an ITU-based perspective, and there seems to be some kind of convergence. May have different interfaces, different software blocks, but certainly from an architecture perspective, there is a lot of similarity to be drawn there. And that is my closing remark. Back to you, Carsten. Thank you.
Thank you, Dave, for the great presentation. I think that was really hard stuff, but it shows that we have a good chance to migrate from DOCSIS services to PON services. And well, it's really hard to see which developments the industry did in the last 5 years. Well, as the next speaker, we have Armin from Nokia, and he is a good guy who knows exactly what is possible for innovative fixed access technologies, and he comes up with the topic next generation PON technologies, and I'm sure that Nokia has plenty of new technologies running on next generation PON. Well, Armin, the floor is yours. Armin, you have to unmute your mic. We cannot hear you. Please.
Sorry. So welcome to this session of ANGA COM today, and thanks a lot for the opportunity to have a short speech about the next generation PON technology of Nokia. I hope you see my presentation. My name, as already Carsten said, is Armin Winter. I'm in Business Development Management of Broadband Networks, which is a division responsible for the broadband access portfolio of Nokia. So, and as you can see, we talk about next generation PON technologies. So, just a second. No, it's not moving. Now it is. So, if you talk about future networks, we do believe that the networks are further evolving towards universal and smart platforms, operated basically in autonomous network, as we just seen, for instance, in SDN. It needs to support different speeds, which are being used by different users, from about hundreds of megabits up to multiple gigabits. Yeah. Each of these comes with the technology advantages which are being made, but also about the different applications which are being run on the network. So traditionally, you may say 100 megabits is more than enough, but the speed is basically progressing over time. And furthermore, users do find always in order to use provided bandwidth. Respectively, new use cases are added, like enterprises, smart cities application, but as well as 5G deployments requiring enormous transport capacity. So the next generation PON architecture, the role of fiber from a poor FTTH to fiber to everything is is provided by converging all services to a single service, single fiber. Sorry. Let's take a look back at the behavior activities during recent COVID-19 pandemic. So everyone was impacted or is impacted by using a home office, schooling activities, or simply high presence of users at home. So it have increased the bandwidth demand for months. So as we see, online gaming increased by 50% or even higher, streaming by 100%, and finally it resulted in a bandwidth increase of 30 to 60%, and in the upstream increase even up to 300%. So the following graph on the very right shows the aggregated bandwidth peak trend during the regular lockdown periods, which will accelerate the GPON upgrade by more than 3 years. So you see, that's already the regular curve for traditional household, depending whether you have a high-end equipment in your home or a low-end. But just by the pandemic and as to speak, to stay at home, it has increased enormously. So consequently, there is a need to invest in the next-gen PON technology. So operators, as Dave said, have worldwide adopted to XGS as the next step towards NG-PON. So XGS-PON has been standardized already by mid of 2016, representing about 10 gig capable symmetrical passive optical network, and mainly defined for application for residential, offices, and mobile backhaul. So backhaul means aggregation of base station. So XGS-PON allow a coexistence of GPON systems in the same fiber, which changed the question for most of the operators at the end from what is the next step to the valid topic, how to do it. So starting from the greenfield areas, we see that if we compare the relative additional costs between XGS-PON and a traditional GPON system, we essentially obtain slightly higher cost for home equipment as well as for network or electronics. While the infrastructure cost, fiber installation, provisioning remain at the same level. So that means that operators starting with their first fiber deployment may consider already XGS-PON technology for the following reason. First, additional costs are manageable. You add revenues which can be achieved through additional offers and use cases, and it's future-proof and at the same time represents a competitive advantage. For brownfield, that means existing install base, it looks a bit different. Here, multiple compatible protocols such as GPON and XGS-PON can be combined, delivered over the same PON fiber, and makes your network 10 gig ready from day one. So coexistence provides a clear benefit to the operator, allowing them to add next generation protocols and incrementally add or convert subscribers in a pay-as-you-grow manner. So finally, you have less cables, less equipment, less effort. Why? Because everything is connected to the same optical feeder. By XGS-PON, you improve also your network efficiency. Due to the higher speed, which can be used for additional services, you may also increase the splitting ratio of the passive splitter, which goes along with cost savings per port. You operate only one network for all application and services, which will optimize your OpEx. Introducing Wi-Fi 6, for instance, you will improve the in-home coverage, so combined with lower latency and mobile offload. And last but not least, you automate your network control and configuration and provisioning and simplify the process by SDN, which is software-defined network. So cost is the mobile operator's topic number one, especially when you talk about any-holing for mobile stations. Any-hole stays for any kind of aggregation of mobile base stations, so there can be backhaul, mid-hole, or front-hole. So therefore, overlaying fixed wireless access on top of wireline footprint, so for a wireline operator, can be a very strategic play. Because the incremental investments in fiber access can also facilitate the small cell densification that is needed to scale out the 5G radio network. So a Bell Labs study, Bell Labs is a part of the Nokia research area, has shown that at least 50% of the fiber cost for 5G any-hole can be eliminated by rolling out an optimized and future-proofed converged fiber network. It is just difference whether you define a specific network or you combine just the network for residential, enterprise, and for mobile aggregation. PON-based any-hole is gaining traction that we see already quite a while. And as you see, since 2019, it's already by 4 more operators planning upon any-hole rollout. So for this purpose, we expect that quite some leading operators will plan for type of any-hole in the coming years. So this is also reflecting looking at the any-hole market view, which is mainly driven by the 5G backhaul and the 4G backhaul. As mentioned before, Bell Labs has modeled different scenarios and different transport technology, and ranging from the new build fiber all the way on the left. In the middle, leasing just fiber, and the second column of the left is even a microwave for backhaul combined with leasing some fiber to connect the microwave infrastructure. at all the way on the right that you actually see, and these use cases we are using as for the existing fiber to the home network. So if you are a converged operator, for example, you have deployed FTTH PON to cover residential subscribers, and if you reuse that network, you can realize significant savings on total cost of ownership with around 50%. So the business case hinges, of course, on the fact that the FTTH network is already in place and you reuse the network, or you just overlay by next-gen PON technology. But you have not only savings on cost for FTTH, but you're also saving time. Why? One of the most time-consuming aspects of 5G rollout will be digging out the street and to install the fiber infrastructure. So if you look at the typical fiber network topology that you see here on the upper right, you provide plenty of residential services provided by the green dots. But you will find also several enterprise represented by the red dots, for which you can provide business services on the same network. So you're basically enhancing your capabilities of your fiber network. Even more, if you think 5G, it's very clear. There will be a point in time that there is a requirement to go into further densification. Installing more radio sites, installing more nodes, installing those nodes will be happening in the streets that you see here. So the blue dots are representing now the cells, and as you see, they are all in the area of a fiber network. So by overlaying XGS PON, for instance, to service business users and mobile cells, we're expecting a faster return of invest by up to 15%. There is still lively debate whether 25G or 50G is the best next-gen technology. So we believe 25G solution is, in our view, the best option for the time being, because it will not only scale for back and mid-haul application, but it will add also the necessary speed to support the front haul. So why is this? First of all, you double the bandwidth. You have true 20 gigabit capacity, and you add a value, for instance, by aggregating 5G transport or additional enterprise services. It's on the moderate cost, for instance, because you don't need tunable lasers. 25 GPON does support coexistence with GPON and or XGS PON, and allow to migrate the technology on the same hardware. And time to market by making advantage of existing the ecosystem of optics. So as you may know, 25G optics are widely deployed for special data center equipment. So the volumes are there, which lowers the price. To continue to evolve your infrastructure into a continuous and serious way, the following properties are crucial for the next generation of optical technology. Above all, simplicity and cost efficiency are key factors for success. So with the 25G PON technology, we achieve this by leveraging the existing mature ecosystem. Simple technology, for instance, no need for tunable lasers, as said before. Coexistence with GPON, XGS PON, or both, and bit rates for tier operators up to 20 gig. Among the residential and radio application, additional business opportunities are achieved by 25G PON technology. So looking at the worldwide business fixed broadband, analysts expecting a continuous growth in the coming years, mainly based on fiber to the premises, as well as fiber to the building application. So the return of investment in 25G PON can be significantly accelerated by the use of converged networks. So one network is more cost efficient on all aspects, beats bandwidth demands for all tiers and kind of operators, and allows dedicated quality of service per service. So while the 10G PON technology addressing the small and medium business application as well as mobile backhaul, 25G PON further enhance mobile any hole and enterprise any further. So you reach 2.5 times more cells or enterprise customers on a PON, of course, depending on the MIMO. You have a throughput per cell increase, again, depending on the MIMO you use. And a full symmetrical 20G can be achieved. And we will reach better SLAs, so service layer agreements, by means of no provisioning or over provisioning of the application that don't apply statical multiplexing, as well as providing symmetrical Ethernet services for enterprise and wholesale. So what about standardization? So early last month, a multi-source agreement has been launched by 25G PON MSA Group to accelerate 25G PON. It's a group of leading customers, leading system suppliers, including Nokia and some others, leading optical and chipset suppliers, and they have formed a consortium to assure that the 25G technology is being standardized, is being defined. The first version of the standard is available now, and it also makes sure that there is an ecosystem so that the operator can really work with different suppliers in order to get the service done and have full interoperability. If we look to the full standardization, the 25G is just away from the 10G to the 50 gig, but by all other technology, it is quite common and fully standardized. Unfortunately, in the ITU-T, the standard activities for which Nokia is, by the way, co-editor, we still see quite some way to go. The technology is much more complex than anticipated, and technical challenge have to overcome with substantial standardization work. Furthermore, the 50 gig for the time being is due to a missing ecosystem like we have for 25 gig. The availability of chipsets, optics, etc., it will be much later, so that we expect a rollout probably not before end of this decade. Yeah, and furthermore, 2 times more bandwidth means by factor more cost for this. Even 10G PON history shows that the 4 times jump in bandwidth needed quite some time. It even quite some years to get mature. So with the 50 gig is now 5 times jump from 10G PON. You can imagine we can expect also here quite some years to go. So in conclusion, the future of broadband is quite simple. Preferably, it's a single network, a single point to multi-point network that allows you to different application, residential, business, or mobile. Allows you to do specific slicing for the different wholesale customers, and this single network needs to be autonomous, most likely cloud-based. In order for you to be able to manage this in a very effective way and to enable anything. Fiber is seen as a single infrastructure that underpins the entire telecom industry and allows a smooth migration from today's GPON and XGS PON towards 25 gig PON with tremendous bandwidth capacity. So 25 gig delivery from the same network will allow you to guarantee anything. And that's the end of my presentation. And I give back to Carsten.
Oh, well, thank you, Armin. That was great stuff.
Just in time.
We worked with 25 gig. Well, for the topic, any hole, we have at the end of this second panel an explanation again what does mean front hole, back hole, mid hole, whatever hole. The other important point I've got here from the chat was a question: do we have to write down our own notes? You can get the presentation with a download link from the ANGA COM website. If you have any issue to get the link, we write it down in our slide decks you saw at the beginning. We will send it by email to your hands. Please come back to us and we will help you. Well, for the next presentation, we have Christian Till with us. He's senior member of technical staff at EXFO, and he has many experience in the world of rolling out fiber optic networks, and he made a great job over the years there. And well, Christian, the floor is yours.
Thank you, Carsten, and thank you for inviting me to this presentation. So as Carsten mentioned, due to my role as a test and measurement expert, we as EXFO get involved from the whole level end-to-end view of the rollout of FTTH. So we see what kind of problems we have with the different technologies, as we've seen from Armin, like the XGS PON, the 25 gig and 50 gig PON. We see the kind of problems and issues you will have with FTTH rollout due to planning issues, quality of components. And so my talk, in my 15 minutes, I briefly want to discuss my learnings and then case studies from the field. So I will do a digestion of different things I have seen in the last year or so, and then to give you an idea on how you can avoid it and what kind of problems you will see. And I'm probably sure you will do some nodding once I mention the kind of things. So for the beginning, I will want to focus on the different problems from both views. So one is the operator view. So if you do a FTTH rollout and as an operator, what I have seen in the field so far is a lack of standardized MOPs. And MOPs in this context stands for method procedures. So how to do the test, what are the thresholds, what are the launch files, etc. So depending on what kind of testing you do, this is not being properly standardized. And that's the problem for the contractor is if you do not standardize it properly, they will do it their way. So like they have been doing it with other customers. So the comparison between the results you get is not ideal. And I think this is one of the biggest things is getting the results in time. And because at the end, you need to have a documented network so you can turn off the customer and have a quality network. I mean, otherwise the customer will leave after 1 year or 2 years when the contract is up, and then you will switch to the competition if you do not provide a quality network. Then we have the visibility issues, so performance overview, status overview, where's the project. If we go further, I mean, we currently see the announcement from Deutsche Telekom, OpenReach, HyperOptic across Europe. Everyone wants to now roll out fiber fast at scale, which means a large chunk of test data will be produced. And managing this kind of data is a challenge. Imagine doing 2 million house paths and you do one test per household. It means 2 million PDF files worst case, which someone has to look at. And I'm not even mentioning the multi-contractor problem. So overall, there's a lack of visibility of the results and quality. If you consider you build a network for 20 years, you want to make sure that the money you spend there is spent into a quality network. Now, if you look at the contractor lens, so the other side, again, the problem of the standardized or non-standardized MOPs, so method procedures are not clear. Contractors have no idea what they're supposed to be doing. It's sometimes a manual execution. And one of the biggest things we've seen is the never-ending admin task. So making sure collecting the results from the expectations, if they go with level deeper subcontractor, then dealing with these kind of things. Repeat truck rolls. So if you're not testing the first time right, the contractor has to do the repair on his own dime. And again, the contract they get and then the money they're getting paid does not cover these kind of multi truck rolls, so they need to be first time right. And obviously we see a lot of competition, so everyone is seeing now this kind of gold rush, so a lot of cheap money there, so competition is getting there, and the contracts are starting to get evaluated on efficiency and need to be faster. So from what we have seen in the general field management perspective is the digitalization is also key for fiber rollout. And from my perspective and discussions with the operators and contractors I have, it's no longer we did it like 10 years ago, we do it still do it, but no, we need to change. And for me, it's a circle of continuous change. And so at some point, you're gonna digitize the test procedures and you distribute these to the technician sub-users. And this kind of job will include everything from the identifiers, thresholds, pictures to be taken, etc. All the instructions are included. And so the technician is no longer spending his time at the unit with setting up the unit, entering the identifiers, fiber ID, cable ID, OLT ID, or whatever he needs to do. But he can focus on the testing itself, be efficient in the testing, and have the right test configs at the right time. And obviously, the biggest pain point, what we've seen, is that 40 to 60% of the time is spent between getting the results back and feeding it back into the system. And ideally, what you would like to have is an automated system where you, the customer buys the internet connection, and automatically through an automation process, jobs will be created, assigned to subcontractors. He will do the test, and as soon as the test has been done, CRM will be updated, and the customer is good to go. And in general, what we also see is the need to congest a lot of data, because at some point you need to update and modify your test procedures based on the feedback you get. So sometimes if your quality of splitters is bad, you need to have this kind of input, and you can only get the input if you analyze the data behind that. And this is key, is that you combine all the test data you get and do your own conclusions, and based on that, we will update again the procedures that are on the test itself. So the management itself from the process is key, and from EXFO side, we have the test flow system, which we have used across Europe with multiple operators, and I'm happy to have any discussion on that afterwards. But basically, the key point is digitalization of the process of the test and measurement. It's key to scale the FTTH rollout. Now, if some of you will now understand or say, okay, I understand the process automation and documentation is important, but actually, what are the best tools to use for maximum input? Well, it depends. And then this is, again, something which we've seen. Each operator will have a different network architecture, will have different rollout processes, different quality of components being used. Is it the splitter quality, the connector quality, where the splitters are located with the PON network. We have seen the XGS PON and GPON overlay can overlay, but again, depending on the architecture, different tools can be used, and I've just put in an overview there. I'm not going to go in any detail of these. You will have the slides deck available, as Carsten mentioned, but I want to focus on three key highlights on what I've seen in the last 3-4 months of a problem securing. So the first point, which is quite big, is the in-house cabling, and this is specifically with the new ones of XGS PON rollout. So we have seen from Armin that the cost of XGS PON to GPON are almost the same. So it makes sense to build a network and test the network so it's XGS PON ready. And the problem with XGS PON is that it uses higher wavelengths compared to GPON, which means it's more affected by macro bending. So macro bending is if you have, for example, in the in-house cabling, which we see here, is that the bending ratio is not, it's too tight to bend it. And the thing what some operators or technicians forget is that the bending ratio, even if you have bent and sensitive fibers, it's different if you pull the cable under tension or it's just laying bare. And it's roughly the half if it's being pulled under tension. So it can actually destroy or worsen your cable and the attenuation of the cable during the pulling itself. And this is why it's key to actually test the in-house cabling. Then if you look at the end-to-end example, typically what we see, 15% of the links fail upon construction, and this is several issues. So making sure you do a proper end-to-end test is key. And then for those of you who follow that, we have the Digital Agenda 2020-2025. We have government funding, which requires certain bandwidth. So now it's required to actually test the data rate itself in order to get the government funding and get the money back. And in the Digital Agenda 2025, for example, we have already the 1 gigabit for enterprise, schools, etc. in it. So we need to make sure that you actually test the data rate and have the birth certificate so you can get actually the government funding. So on so the video was not playing, apologies for that, but what chat is installer we have interviewed, and he's confirming that when the wiremen are actually pulling the cables, if they could verify it's all correct, it would lead to a lot of less errors on our hand when we're trying to finalize and hook up everything. Because again, this is an example of doing the last mile and doing the cable pulling, which results in a lot of problems. And what we have seen as an efficient tool is a new product category. It's called OFM. It's optical fiber multimeter. In terms of where it stands in the general landscape, I mean, it's between the power meter, which let's see less and less use cases for, and more between an OTDR and the power meter. So it gives you a single in a test, and actually it makes sure that the full in-house cabling is properly done. So you do not have any kind of macro bands, that the optical connector at the outlet is properly. So this is another issue which we see, is that the connectors here are dirty and scratched. So you want to make sure that you test this one. Macro bands will occur here or during the pulling. And obviously you also want to make sure that you do not have any breaks in the living unit, because otherwise you will have a bad customer experience and therefore more changes in the customer itself. And the quality of network, it's a key thing to keep the customers happy. And it's again a single line test, so you can verify in 3-4 seconds. Length, ORL, which is important for higher bandwidth, and loss. And from there you're good to go, and you are good to go to hook up the connector and then the end customer. Now, if we look at so this was more on the in-house cabling. Now, if we look at end-to-end tests, as I mentioned, 15% of all links will fail. So there are different tools and then different things you can do in order to make sure that the end-to-end connectivity test is properly done. On what we have seen recently in the last year or so with multiple operators, it's a centralized OTDR, which is being installed. And the beauty with a centralized OTDR is that the technician who's out in the field does not need to have any equipment at all. So you have the CapEx cost inside the CO. And depending on, again, on the network architecture, the centralized OTDR can be hooked up to the coupler if you do multi-signals. And then you can test the up to the splitter, the F1 fiber, as we call it. And as I mentioned, less or no equipment is needed. So the technician itself, if he wants to verify the splitter, he can simply use an HID, connect it, and test it. And everything will be done through a phone app. So the phone through the cloud will be controlled, and it will jump to the correct fiber. And you do cross connection stack. You can check the distribution fiber and also the end-to-end. So you check for cross connection and end-to-end loss. The other equipment we have seen is the using the OLT as the identifier. So basically the question is, at the end customer house, you want to verify at which OLT port you're connected to in order to make sure that the white labeling of the ONT is correct and that you know that it's connected to the right port. Now, few operators, one in Germany is doing it that way. So he's connecting an EX1. Due to the GPON ID and the GPON frame, there's some information inside. And inside the header of the GPON frame, for example, the TX power of the OLT is inside. So with the device, we can then read the OLT power from here. We can obviously measure the RX power here. And from there, it's calculated then the total optical loss. So I have an end-to-end loss calculation based on the information from here. And if it's activated, it will also transmit the GPON ID. And this is something which is customized by the user, by the operator. So the operator will know this kind of ID would correspond to this port. So I know the end-to-end connection is available. And for this one, you can have the end-to-end connection check. There are some drawbacks which I'm not going to go into. Happy to discuss it afterwards. And last but not least, I mean, the same unit, and you also need to do the pocket-sized residential business use service turn up as speed testing. So making sure you generate a proper birth certificate, and the unit which is so here, they're different available, but basically you can do Wi-Fi, RJ45, so LAN, and also optical test. And you will do the speed test, and then you have a proof and a birth certificate, and then can go to the EU government or to the local government to get actually the funding approved. Because then you say, okay, this customer here at this speed, and maybe you see that, but this speed test is the typically one the customer's doing as well. So we use the UCLA speed test in the background, which is basically speedtest.net. But there are some drawbacks if you do it with a local PC, so it's always recommended to have a dedicated test device on that.
Christian, please take care of the time.
Yes, I was just finishing and rolling up. So just to summarize, digitalization is key, and having the right tools for the right build out is key. And you need to make sure that get in touch with us. We are happy to explain and give back our experience from what you've seen. And with that, I'm done.
Okay, thank you, Christian. That was a really great presentation that shows how many work we have to do to make such an optical network happen up to the customer, and that we can serve the provided bandwidth. Well, just for your information, we copied the download link for the presentation that will be tomorrow available here in the general chat. Everybody can copy the link for the download area. And well, I have the good news. It's like with football games. We have more than 500 participants here in our session. I'm really deeply impressed, and I will thank you to our panelists. They do a very good job. And well, next speaker is Jan Backman from VXFiber. And VXFiber is a very innovative startup, and Jan worked a long time for VXFiber, and they use the bandwidth we already have here. And well, Jan, please explain to the audience how we can use it in a good way for our customers. The floor is yours. Thank you.
Thank you. And first and foremost, I want to again express my gratitude for being on the panel. Thanks a lot to the organizers at ANGA COM, especially you, Karsten, and for having us and having VX on the panel. So it's been a long afternoon. I'm just starting this presentation. I think it's the number 4 in this panel. So why should you listen to this presentation? Well, if you are a fiber owner, if you're a utility company, if you are an energy company, if you are a city or other type of fiber owner, you should listen to this. We want to cooperate with you. We think that that's what true open access is all about. If you are a carrier, an altnet carrier, a small carrier, or a medium-sized carrier, it doesn't matter. We want to cooperate with you. So that's why you should listen, and I hope that brings us to the next topic. Very briefly about VXFiber. We are a fiber operator on a wholesale only operation type, and we're also a fiber investor. So we both invest and operate networks. And true open access for us is basically complete open access, where all types of ISPs are available and welcome. We have a long history. The company is only 5 years old, but most of our management team has been working for almost 20 years in the fiberization of a couple of markets, especially Sweden. That's our home market, it used to be, and now we're fanning out to other markets like Belgium, UK, Germany, Austria, and South Africa, to name a few. So I won't dwell on that except for the last point. We are part of AMP Capital since September. So that is our main owner and investor. It's a company with deep pockets and the possibility to invest in infrastructure all across the world. So what are the trends then in terms of separating the infrastructure from the operational layer and ISPs? So we believe that the ownership of access infrastructure is a key factor for a number of companies. If you look at the tower companies of this world, like Deutsche Funkturm or American Towers or Cellnex, they do this already. They separate the infrastructure from the operations. And Liberty Global only just recently, I think it was in October, announced that they will actually separate their whole cable network, basically to offload the balance sheet and to open up also to finance their fiber rollout, which is the next generation. So there's, as we see it, less need for an infrastructure competition in each section of a network. It doesn't make sense to overbuild. The relevant distinction is really between the infrastructure and the service, and they have completely different time horizons and also then different investment horizons. They need to be treated separately. The operation needs to have scalability. You need to scale to be able to succeed. And how we do it, or other in our industry does it, is to basically virtualize the access layer, blurring the line between the active and the passive layer. So using software to basically virtualize the hardware and the active equipment, so that we can share the active equipment, not just a couple of them, like in the bitstream scenario, but many ISPs. So since the investment horizon and the complete competence buildup of an operator is completely different in terms of the active layer and the passive layer, this is why we separate them. So we focus on network utilization, getting as many customers on board as possible, using as many ISPs as possible. Different ISPs cater to different needs and to different types of customers. That's the only way to get the investment back. That is the only way to look at the passive infrastructure, to maximize it so that 70% use it instead of maybe 50%, 40% take up. So how does this work in, so to speak, the theoretical world? The EU has defined a couple of models. From the left, the traditional vertical model, which you would know from a traditional operator, all the way to the right to something we call three-layer open access model, 3LOM. That is the model that we are using. The bitstream access model, which is the second from the left, is where you basically sell off your wholesale capacity to a service provider, maybe one, maybe two, maybe a couple. The passive sharing, which is the one next to the right, is something we see, for example, in Switzerland or in other areas of Europe, where each service provider basically brings much more equipment to the table. What we do in the three-layer model is we completely separate the fiber owner from the operator side, and the ISP layer, which is the one interfacing the customer, that is completely separated and run by many ISPs catering to different needs. So we are taking care of the midsection, which is the market portal, the sales portal, and the fiber operations, which is active equipment, etc. So what is that exactly? What do we do? What does a three-layer model operator really do? So we design the active network layer, the complete architecture. We develop and we run the software, the BSS, the OSS system. We manage the sales portal, making the ISP able to address a large market efficiently, automatically. All of the operations are done automatically, no people involved. So we run the network, there is a NOC, we maintain it. We also operate the backhaul of the network. and have the contact and the contracts to the service providers who supply the end user services, be it any type of triple play. And that is especially interesting for the smaller and the medium-sized operators, the third, second, potentially in the long run, definitely also the first tier operators, the big ones. So how does that really play out in real life? Looking at the midsection, what we do, as I mentioned, is the backhaul, the active layer, all the access switches, all the technology that you need to have in place. The software, the BSS, the portal that is completely integrated into one integrated system. And that we do for the passive infrastructure owners, where we pay them the rent. So the service provider basically only have to focus and concentrate on three things: sales, marketing, and product management, really providing the service and the product to the end user, be it telephony, broadband, plain vanilla, or TV-like services. So this is the three-layer model with a network company, a NetCo at the bottom, OpCo, which is us, VXFiber, and the service provider, the ISP, at the top, closest to the customer. So this is a way to really do a process and value chain re-engineering, and this has been done in a couple of markets, and I will show you some of them. So where does the money then flow, so to speak? In this case, from the left to the right, from the end user all the way back to the fiber owner. And this is what we wanted to achieve: the highest possible utility, the highest possible take rate. So the subscribers will pay their connection fee, their subscription fee to the service providers, which will sell them all types of services, also have the customer care, the customer contract. Us as a three-layer operator in the middle never have any end user contacts in terms of subscriptions. The network operator, that is us, then operate the complete active infrastructure and pay the fiber fee, the rent, back to the fiber owner. This fiber owner could be a consortium, it could be a co-investment where we co-invest, it could be a bank, it could be other types of investors in the end, or it can be a owner from the energy company or utility company. So how does this then differ from broker platforms, from bitstream access solutions on the market? Well, we try all the way to the right to tick all the boxes. So one of the most interesting things is that we completely separate all services through virtual LANs, which makes it possible to buy one service, broadband, from one operator A, to buy the telephony from operator B, and to buy the TV from the operator C. So completely making the structure open and to maximize competition between the different service providers and the different platforms in terms of products. The broker platform is helping the bitstream access wholesale hold buy process, definitely, but it does not provide what we provide in our platform. And bitstream access is similar to what we do to the left in this picture, but it's manual, more manual process. It's a more bilateral process, and it's something that provides you not with a complete automation and not the possibility to completely separate services. So when we say open access, we say complete and true open access in all aspects. So how does this work in real life? For example, in Sweden, in Austria, in Germany, in our first network there, in the UK, where we are also building, or in South Africa. This is one of the examples. This is Vumatel, which is our partner in South Africa, with today more than 200,000 active customers, where we grow at least 5,000 every month at this stage. We achieved from 0 to a little bit more than 40% of the market, a market share, starting with smaller operators. And actually we have more than 60 operators, small and medium-sized and large operators, on the same platform, sharing the same active layer. Not just 2, not just 4, but 60. Obviously not in all segments of the industry or in the market, but we are sharing one network, starting with a small, and actually today also having the Vodacoms and the Telcoms joining us. So bringing basically a very broad platform portfolio to the end users, bringing broad value to the customers that we supply with these services, and also bringing value to the network owner, which is VUMA or VUMATEL. So getting to, so to speak, the conclusion, how does this work and how are the benefits to be reaped? So what we see, open access, there's a lot of talk about open access in different formats, in different forms. But open access is not the same as open access. What we define as true and complete open access is wholesale only infrastructure, where there is not just one service provider building and then selling off the free capacity on the side, but really being completely open and neutral, net neutral from the beginning, from scratch. And also what's the prerequisite for that is software-defined networks. So we really can share and virtualize the complete active layer, not just bringing your own equipment, like in some of the bitstream cases, not just bringing even in passive equipment, in the passive sharing scenario, but sharing one active layer, which is the most efficient out of a cost perspective. The active layer being roughly 15% of the investment and the rest being passive. So we will optimize costs, we will optimize consumer choice in the complete value chain, and first but not least, and pushing up the utility rate and the take-up rate of the network. And that's the only way in the end that you can pay a good rent to the fiber owners or the bank. So mobile tower companies and even some cable companies, which I mentioned, Cellnex, the American Towers, also even Liberty Global, they are leading by optimizing their value chains. So they're renting out the infrastructure to maximize the long-term business case. And these operators also, they would need money to invest in the next generation networks. That's why they also offload their balance sheets. That is done at the same time. So also giving them the possibility to focus on differentiating services, getting innovation into the ecosystem, getting smaller ISPs, specialized, for example, gaming ISPs or ISPs with a certain language support in their customer care or other types of ISPs. So we believe that this has started in the end with the smaller operators and the medium-sized operators, but we will see this coming into tier 2 and potentially also tier 1 operators over the coming years. One of the tier 2 operator in terms of a European size, Telia in Sweden, already since almost 10 years is running a completely open network. And that has been, so to speak, for them a success story. And during that time, they also fiberized the country and considered also being still number 1 in the market, even if they have an open network, letting on competition to their own network. So what we need to do is really to reinvent the value chain in order to accelerate wholesale and corporations. We see corporations springing up all across Europe at this point. Even in large markets like Germany, we see the likes of EWE-TEL and Deutsche Telekom cooperating, which is something that didn't happen a couple of years ago. We see some of the big players opening up, their wholesale departments growing, and we see definitely that the regulator is looking into this, and if the market doesn't open, there's always the chance or the risk, depending on how you see it, of regulation opening up and forcing an opening up of the market. Where we see overbuilding infrastructure, that does not make sense. Core markets in Europe where there is less than 10% fiberization, and there are a couple of them, it doesn't make sense to spend all the money trying to compete in the same area. So overbuild doesn't really help it, doesn't cut it. What we need is more cooperation and efficient cooperation in a way where the market forces can work for you as a fiber owner. So we see more, and we're going to see more of corporations. These business models, these platforms, these technical platforms are available on the market. They are even in tenders in, for example, in Austria, in Sweden, and elsewhere. And we see now that investors, and even, as I mentioned, the regulator, is starting to demand more openness, to demand more open networks for the utilization, and of course getting quicker to the end user, and getting a portfolio of end user services to the market quicker. We see that the trend is clear, and we believe that the fast will eat the slower players in the end. So that leads me to, I guess, the final conclusion, and that is that fiber networks, FTTH and open access, is like gravity, and we've seen it in South Africa. If you are very big, you can perhaps resist gravity a little bit longer, but in the end, it will get to you. And this was actually a quote by our dear Anthony Whelan of the EU. So thank you for listening. I hope that there will be some questions at the end, and hope to see you all at the real life event, ANGA COM, next year in Cologne, and hopefully we'll be there and safe and sound. So thank you, and over to you, Carsten.
Yeah, well, thank you, Jan. That was a great presentation, and it shows how the regulatory work will go on here in Europe. And thank you again for the last slide you have here. For sure, we will see us next year at ANGA COM, and we have a Kölsch and some face-to-face meetings. I miss it very much, and I'm sure that we see us there. Well, as I said, we have a very short question area right now here, and I have one question here coming to Armin. Armin, hopefully you are prepared. The question is, does 25G PON uses coherent optic technology? I know coherent optic technology is a very, very hard stuff. I think we can have a complete session on it, yeah, a full day session, but maybe you can answer this question with a few sentences.
Yes, sure. Indeed, it's a new technology, and there's always a debate in regards of, let's say, the practice that you're going to use, the pinning that you need for the control of the optics. So at the end, we brought that also to the standardization to use SFP28 type of devices, which means they fit into SFP cages. Yeah? And what's the benefit? It is because you could just complement existing hardware by the SFP 25 gig optic, so that you can easily migrate to the next gen. Yeah. So SFP28, I think, is getting or become a quite common standard for that. From that point of view, I'm optimistic that we have here current optical technology available.
Well, I fully agree with you that that will the way we running down, that we go to coherent optics. Well, we have also some questions regarding the XHAL. From my perspective, we should put this answers to the end of the session when we had also the presentation from Robert there, which brings me to the topic that now, Mike, your second panel will start, and now you are in charge. Please do it in a good way. Good luck.
Thank you, Carsten. I will try my best. Right, we have 5 presentations to get to now. The first one is going to be given by Dr. Friedman Weib. He's the Director of Product Management at HUBER+SUHNER BKtel. He having spent over 10 years as Director of R&D at BKtel before the acquisition by Huber and Schuner. So, Dr. Weiss, it is yours.
Thank you, Mike, for your kind introduction. I try to set up everything. Okay, hopefully the screen can be seen. Welcome everybody to this first presentation of the second session. It is about optical nodes supporting emerging and future technologies. And this presentation builds kind of a bridge between our first session, where a lot of presenters have elaborated on PON technologies. We will also answer the question at the end how the optical node can support PON networks. And this presentation is presenting the optical node as, in general, as a future bridge, to future technologies. We will elaborate on DAA, on DOCSIS 4.0, and finally on PON. Before stepping into the first technology area, DAA, please allow me to stick a bit to this pole position of the optical node as a future bridge. The clue is that optical nodes have always been the MSO's bridge between the newer fiber optical part of the network and the elder traditional coaxial part of the cable network connecting all the subscribers. So it is quite natural that the node has the ideal pole position also for future technology, which of course has to do a lot with fiber technology. It is clear that at the node position, we have fiber infrastructure available. And moreover, in many cases, we have other benefits as well. Typically, the node position is co-located with power utility access. So we have some room, some space for increased power consumption. We have physical space, as we are typically in cabinet installations, so room for extensions. And for example, in case of the German network, we have a modular node architecture giving options for reconfigurations. Well, what about DAA? DAA is the first future technology we would like to discuss here. DAA stands for Distributed Access Architecture. And the idea is a revolutionary idea. Change the analog optical transmission technology in the optical fiber part to digital optics. To do so, we need to separate a former part of the CCAP and move it to the node's position. This part is the physical layer. The modulation and the demodulation must be moved at the border between the digital optics and the coaxial network, because the coaxial cable is still an analog media. So we need this analog technology here at the remote position. Thus, the technology is called remote PHY. It is not so easy to do that, but there are many strong drivers doing so and introducing digital optics. It is not only increased bandwidth, because we have a higher quality in the coaxial cable network. We can exploit it better. We have also a more efficient head and space utilization by that when we move parts of the CCAP core outside. And last not least, a very big motivator is service convergence. Once we have a converged interconnect network here, we can not only run DOCSIS service, but also other services like business services. Let me spend another slide on this benefit and talk about a bit about the converged interconnect network we have now in the fiber topology area. This digital optics is standard 10 gigabit Ethernet technology, and thus it can be used also for business services, for example. But there's another benefit. We can cover bigger distances with this optical network right now. An example is depicted here below. We have homologized a technology where we can run up to more than 80 wavelengths over one fiber and cover distances with optical amplifiers and dispersion compensating modules. So we can realize up to 130 kilometers of fiber spans. So Summarizing it, DAA technology, distributed access architecture technologies, both remote PHY and SYN technology, is ready for implementation. It is not the end. Vendors are investing into further technology generations. So it is up to the operators to decide which and when to adopt a generation. A second new area of technology is DOCSIS 4.0. Now, DOCSIS 4.0 is prepared by node vendors, and actually we are discussing here about 3 sub-technologies. They are called or abbreviated with FMA, ESD, and FTX. And what they all have in common is that the final time schedule is a bit dependent on chipset availability and on the quality, how these technologies are implemented. Let me elaborate that and explain that by the first buzzword. FMA stands for Flexible MAC Architecture. And the idea is not only to move the physical layer out into the node location, but also the MAC calculation. Why? Now, by doing so, we can speed up network latency. We can lower the network latency, which might be required by future applications. Think at autonomous driving, for example. And so industry already prepared itself for these lower latency requirements that might come up and defined the flexible MAC architecture standard within DOCSIS 4.0. We already have first implementations on the market, but to do it in a cost-efficient and in a power-efficient way, we still have to wait for chipsets. It is possible for node vendors to prepare their architecture such that when the chips appear on the market, that then vendors are quite fast to adopt these chips and to come up with this technology. The same is true for the second subset of DOCSIS 4.0 technology called ESD, Extended Spectrum DOCSIS. This stands for using the coaxial network up to 1.8 gigahertz. It's depicted on the right side. Downstream is going up to 1.8 gigahertz. Now, this is nothing special in RF engineering. Using frequencies up to 1.8 gigahertz is nothing special by itself. But again, the clue is doing it in a cost-efficient and also power-efficient way. That's why chip vendors, RF amplifier chip vendors, are in prototype status right now and announced chips for next year. So again, node vendors can prepare their node implementation right now to be very fast and to come up with products as soon as the chips are really available in series. There's one important remark. When we want to apply and to operate coaxial networks up to 1.8 gigahertz, the network might have to be redesigned. I don't want to elaborate on that because we have further presentations on this topic today in this session. Finally, there's a third area, FTX, full duplex operation. This means that the coaxial cable is used in parts of the spectrum for both, for downstream and upstream transmission. This is quite a sophisticated thing to operate, and it's maybe a bit later in time schedules, especially because it requires an N+0 architecture, so it requires a purely passive coaxial network. Okay, last topic to be treated by our presentation. How can nodes support passive optical networks? I think we all believe that pure fiber networks are most future-proof and that the trend will go towards optical fiber. And the important thing we can state is that digital optics, DAA technology, remote PHY, SYN technology, allows an easy migration and extension towards PON. The first and very straightforward idea is just to extend the SYN network by a PON. And I've depicted on the left side an example. What you see here is a 10 gigabit Ethernet switch in a form factor that is compatible to be implemented into node installation. And we can put this 10 gigabit switch, it's available, into a fiber node and run and operate, for example, point-to-point networks for to connect small and medium-sized enterprises. So we could provide 1 gigabit or 10 gigabit Ethernet downlinks to serve business customers. Another idea is to turn this 10 gigabit switch into an OLT, remote OLT, and span a passive optical network, a GPON or an XGS-PON network, for example, to connect a fiber network. Or third idea is again turning this switch into an OLT and connecting via PON many DPUs to serve fiber to the building structures. So this is quite straightforward. Let me finalize by remembering an elder technology called RFOG, RF over fiber. This technology is around 10 years old, and in those days it was defined to operate DOCSIS or to run DOCSIS via PON networks. In those days it has been DOCSIS 3.0, and I would like to add some update remarks. We can still use RFOG technology today. For example, by running a fiber island, a PON island connected to a copper part of the HFC network, so connecting it to coaxial cable. We would need an inverted fiber node and of course RFOG fiber nodes at subscriber location. And today we can implement this technology also with DOCSIS 3.1. So the specification, which was 10 years ago, is updated today towards DOCSIS 3.1. The standard describes operation up to 85 megahertz upstream, but with some tricks and limitations, we can even run 204 megahertz OBI free over such an architecture. Second remark is that today we have diplexer-less RFOG fiber nodes available, so that we can move seamless between, for example, 65 megahertz upstream, 85 megahertz towards 204 megahertz. Finally, a bit of a warning, DOCSIS 4.0, namely ESD and FTX, are not recommended because we have to think that RFOG technology still is an analog optical transmission system. So I would like to thank you for your attention, and hopefully you agree that the optical node is really the key element to build the future. Thank you.
Thank you very much, Freidman. Now, this really rather nicely leads us on to the following presentations that are coming along next. So our next presentation is going to be by Artu Permanen, the Vice President at Teleste. Before devoting his efforts to technical marketing, Artu served as a business director, product manager, and general engineer at Teleste. Understanding the customer perspective has always motivated Artu, and his latest research work focuses on customer retention rates, especially the question of how operators can use intelligent network products to prevent churn. Artu, the floor is yours.
So hello everyone. and thanks for the opportunity to talk to you. Today, I'm excited to share our latest test results. We have just completed 1.8 GHz amplifier and amplifier cascade tests, and based on the test results and also solid theoretical background, we can show how good RF amplifiers cable operators will have once 1.8 GHz network upgrades start. Decade after decade, cable television industry has seen several network upgrades. To us, the next upgrade is just one wave before the next one. We do not see any reason, not practical or theoretical, why 1.8 GHz wave would be the last one. Coaxial cables have said operators who ask so-called one-digit network upgrades. So in that sense, we do not see fiber to the home initiatives competing with the existing coax-based networks. Rather, we would like to see competition focusing on services and service quality, not the medium that is used to deliver those services. However, we have seen changes causing challenges in the past. New, more advanced modulation methods carrying more bits per symbol require higher modulation error ratio. Higher frequencies and loads have led to higher total composite power, TCP, which challenges margins and again requires better mirror. On the other hand, so far all these challenges have been solved. Now we have more robust modulation methods and improved forward error correction methods. Amplifiers are better and more intelligent, and the digital fiber is currently replacing old analog links, meaning that our source mirror in the input of the first amplifier is better. Decade after decade, certain things have not changed. We will have engineers who say that the next change is different and more complex. I do not even propose fixing that issue. As I'm an engineer myself, I feel that I have all rights to say that every engineer wants to solve complex challenges. Often engineers are so convincing that even others are starting to believe in them. However, also another thing has not changed, and that is the distance between street cabinets. All those different distances that we have in the field require us to plan networks carefully. But also better amplifiers are needed. But it's easy to say better, but what I actually mean with the word will be explained in the coming slides. At the same time, we look an answer to the question if 1.8 GHz networks require additional booster amplifiers between amplifier stations. Cascading 1.8 GHz amplifiers and reaching 4K QAM can be trivial if the distance between amplifiers is chosen without limitations. In such cases, measured results follow the 10-log equation, basically meaning that theoretical calculations and measurement results are equal. However, in practice, some of these cascaded amplifiers would be extender amplifiers in new locations, and often operators are not eager to have new active devices in new locations. As attenuations in this more theoretical case are low, every amplifier can have low gain, leading to excellent carrier to noise ratio. Thus, also measured MER in the output of the fifth amplifier is outstanding. But what happens if we remove those new locations? Now total distance is the same as in the previous picture, but we have 3 amplifiers and the distance between amplifiers is doubled. This leads to higher gain and lower carrier to noise ratio. Now measured MER in the output of the third amplifier is 38 decibels, and actually we cannot use 10 log equations anymore. What we have found out is that in these kind of cases, results follow about 13 log equation. And if we would increase gain even further, leading to higher TCP, the equation would again move a step towards 20 log. In this picture, we can see those 2 points that we just measured, or what we have measured. Our horizontal dimension is amplifier gain, equaling with the attenuation between amplifiers, and vertical dimension is the number of cascaded amplifiers. And please note the logarithmic scale on vertical dimension. So let us measure more points, other cascade lengths and other gain. We know limits of MER being over 41 decibels if we want to use 4K QAM, while 2K QAM requires around 3 decibels less, and again 1K QAM requires 3 decibels less. These lines show you how many amplifiers you can cascade when TCP does not exceed 70 decibel millivolt. So for example, one amplifier has enough good carrier to noise ratio if you want to use 4K QAM, and TCP is 70 decibel millivolts. While you can have the same gain and 4 cascaded amplifiers if 1K QAM is used. It should be noted that these lines describe limits. Everything below them is easy. For example, if the gain is around 25 decibels, like we had in our earlier example, number of amplifiers is not a problem from technical perspective. However, it is very likely a problem from total cost of ownership perspective. So as a summary, I would like to say that coax has served us well. We have seen challenges. New challenges will surely arise, but they will be solved. When we come to 1.8 GHz network upgrades, the attenuations between amplifiers will be guiding us, not number of cascaded amplifiers alone. Today, and I want to highlight the word today, 1.8 GHz amplifiers can manage 70 decibel millivolt TCP. Within 1 year, that figure might be higher. Historically, operators have wanted to avoid new locations where we would have new amplifiers. We can see that careful network planning, overall technical awareness, and intelligent amplifiers are ways to limit such locations and keep networks adaptive. I want to thank you. So please, Mike.
Thank you, Artur. That's interesting. I'd really like to see an amplifier running at 70 dBmV. I have not seen one in my time, but it's something to think about. Right,
come to Finland and you will see it.
I will do that. Thank you. Right, we move on now to our next presentation. Now, the next presentation dovetails quite nicely into the one that Janice has given. And our next presentation is going to be given by Jan Allison. He's the Chief Technology Officer at Technetix. Jan has an experienced engineer. He has over 30 years in the cable industry. He currently leads the CTO, marketing, PLM, R&D, and QA teams at Technetix. My word, that is a lot to do. His main focus is to liaise with key customers and be the Technetix technology advocate, developing new technologies and product platforms. Jan, the floor is yours. But we have no microphone. I think you need to unmute your microphone, man, Jan.
Yes.
Well done.
Sorry. Sorry. Yes, thanks, Mike. Thanks for the and the ANGA that I can have this presentation to show to all of you. My presentation will be in the will be around what can we do for DOCSIS 4.0. So I think also what Arthur said, DOCSIS 4.0 have a number of challenges, and I would like to go to those challenges and give you some solutions for that. So what is the step after DOCSIS 3.1? What are the options, the challenges, and the solutions? And especially I want to have compare the network options, to compare the high power amplifiers with high gain, the normal amplifiers in combination with booster amplifiers, and a new architecture called distributed gain. What we see, what's happening after DOCSIS 3.1, and I think we have a number of options. What will be the next step? Everybody at the moment is rolling out DOCSIS 3.1, and there's still a lot of life in DOCSIS 3.1. But it is good to know what is the next step. What will be the step after this? And I think the next step is that we have extended spectrum DOCSIS. We can go to full duplex DOCSIS. We can go to frequency division duplex, or we can go for distributed gain architecture. And in fact, if you look to those technologies, you can see that extended spectrum DOCSIS and distributed gain in fact fits in the same group, and the same with FDD and FDX. But if you look much closer going forward, I think at the end they all end up in the same group, because it will be a mix of different technologies, all what will happen after DOCSIS 3.1. So that's needed, because what we want to have is we want to drive that 10 gig goal. That is the goal, but what is the right technology to choose from this? So I want to go quickly through this. What is extended spectrum DOCSIS? What does it stand for? In fact, we go from 1.2 to 1.8 gigahertz. And the upstream, we can go to even up to 684. But it has a number of challenges. How do we overcome the additional loss on those high frequency signals? Because at the end, the coax is as it is. The amplifiers are on this position. So can we drive high enough to overcome the additional loss? And then we have to think about what is the total composite power of the transmit amplifier. Because yes, we can drive higher levels out of the amplifier, but the TCP on 1.8 at the moment is not as good as we can achieve on 1.2. And even then, if you look to a normal link, then if you make the step from 1.2 to 1.8, you roughly need around 15 dB more level. And there is no way you're going to get that 15 dB out of your amplifier. And then the other point is, if you cannot drive this high enough, you will have noise issue at the receiving amplifier. So in fact, the only real answer you have on this is amplifier respacing. So what can we do to overcome that? And can we drive high quality signals to reach the homes? If we want to achieve 4K QAM, we know that we have to have a carrier interference noise of 41 dB. And we need a minimum input level on the CPE devices of 0 dBmV on the downstream. So that is a real challenge to be able to drive 4K QAM. At the moment, it's not possible. The hybrids are not good enough. And even when you go for double power consumption and you will look into amplifiers with 48 dB gain, for instance, it only will increase the OPEX and it only will lower the lifetime. Because you put so much power inside that small hybrid that overall the MTBF will kick in and your failure rate in your network will only increase. And if there is one thing important in the future is what can we do to reduce the OPEX, not to increase the OPEX. So that's the challenges for the extended spectrum DOCSIS. If you look to frequency division duplex, what is that? Is that in fact that we have normal traditional communication where you have an upstream and a downstream. Now you can have them mixed. You can have upstream, downstream, upstream, downstream. That is what they have for the future, and that sometimes is needed for maybe FM radio, or maybe you have a downstream carrier around 100 megahertz that you need for your CPE devices. So that is a challenge. How do we do that? Because what do we do with the dieback filters? Because it will be very difficult to make a dieback filter as upstream, downstream, upstream, downstream. And then, of course, what to do with all these crossover areas? Because you can see there is a lot of white space between all those different bands. And that is, of course, a frequency you just lose on this guard band. If you look to full duplex DOCSIS, then you have a set of traditional. Now you have a certain area where you can have upstream and downstream on the same time. So that means that you can have upstream traffic on 100 megahertz and you can have downstream traffic on 100 megahertz. And of course, that is perfect to use to have the best possible use of your bandwidth on your coax. But you can see we have no guard band, and because we have to have the double power, double direction, we cannot use any diplex filters anymore. So is this a must N+0? You saw on the two presentations before is that if we want to go for full duplex DOCSIS, N+0 is one of the big questions. Is it absolutely needed to go to full duplex DOCSIS? Or can we take the diplexers out and can we use echo cancelers in that? And yes and no, echo cancelers can help because echo cancelers can replace diplex filters, and that can help you to create an amplifier without diplex filters. But the downside of echo cancelers is that they will have an insertion loss of around 5 to 6 dB. And that means if you have one on the input and the output, and you normally have a 44 dB gain amplifier, you're going to lose 12 dB already in those two echo cancelers on both sides. That means that your amplifier, instead of a 4 dB gain amplifier, is suddenly a 32 dB gain amplifier. Next to that, your noise is 6 dB higher, and your output power is 6 dB lower because you lose on both sides in the echo cancelers. So yeah, theoretically this can work if you can overcome that loss. And then the last thing is, as you saw in the previous slide with the circle, can we have a mix of all of this? Can we combine all of this together? And then, is this feasible? Can we combine extended spectrum DOCSIS, FDD, and FDX all together in one part? So then, in fact, you end up with a signal like this, where you have upstream, you have a part where you have upstream and downstream simultaneously in the full duplex area, and then your whole downstream will even go to 1.8 gigahertz. That, of course, will be the perfect answer if you want to go to your 10 gig goals, because now you'll have a lot of bandwidth on the downstream, but also still a lot on the upstream. And then maybe the next step is this also then the route to 3 gigahertz? We saw on the SCTE a few weeks ago that there was a lot of questions about what is the step after 1.8? Is the 1.8 is then a 3 gigahertz step? So can we then even combine this with even to go to 3 gigahertz? So we did a lot of research for that, and one answer to this is what we believe is distributed gain architecture. So distributed gain architecture, to give you an overview of what that is that you have normally you have 3 amplifiers, let's say an N+3 or N+4, you have 3 of those amplifiers. If you want to go to a higher frequency, you need to go to a high gain, a 48 dB gain. We see this in all the slides. But 44 dB gain means double power consumption, a critical MTBF, and you will have a lower quality signals. You can also see this in the previous presentation that the MER will be reduced, so you cannot reach the 4K QAM anymore. So you have to step back. So you are increasing your bandwidth, but you are decreasing the number of bits you can put in that bandwidth. Another option is, can we use normal amplifiers, like normal 44 dB gain amplifiers? But because the cable is too long, can we put in a small booster amplifier to gain the signal that it can reach the next amplifier? So that small amplifier will help the first amplifier because you don't need to drive so hard, and also helps the second amplifier in this example because the input levels are higher, so you stay out of the noise. So this will not only give you a network that you can have normal MTBF because you don't have to go to this high double power, but also you are increasing the quality of your signals because you stay out of the intermodulation and you stay out of the noise. And then the last part is distributed gain. And distributed gain, in fact, is that we don't go to those big amplifiers, but we just go for small amplifiers and we keep the signal alive over the network. That's the idea. Can we just have a number of small amplifiers all in a cascade that every time we have about 20 dB gain and we don't have to go to the high levels and we stay out of the noise? That's the only thing we do in this. We stay out of the noise and we don't drive it hard. And you will see that overall you will have a much higher quality and a lower power consumption. This was not our research. Shaw in Canada did research on this, and they looked to this network where they had an N+2 network, amplifier, they had 5 taps, amplifier 5 taps, and they have roughly around 60 meters of coax between the devices, between the amplifiers and the taps, and between the taps, etc. And then they compare the different scenarios. So if you have high power gain, like you have on the left side, then you have the normal amplifiers, the same locations, but you go to high power, and you can see on the line below that we need to have that green line to be able to deliver a good signal into the homes. And you can see that more than 60% of the homes, in fact, are failing. So more than 60% of the homes cannot receive a 1.8 gigahertz good quality signal. So we have to reduce our, in the left example, you have to reduce the modulation scheme a lot to be able to deliver even a few bits on that frequency. So that high power amps is not really a good solution if you look to the quality and the levels. If you go for the normal, the middle one, where you have the normal gain with the booster amplifier, then you see that we have roughly 20 to 25% of the homes suffering that we don't have enough level. So this is, of course, a huge step forward if we go from 65 or 65% failing to 25% failing. But if you go to DGA, you can see that on the right side, there you can see that all 100 homes, in fact, have enough signal, not only to do 4K QAM, but we even have enough signal to go to 8K QAM if we want to. So you can see that the distributed gain with small amplifiers absolutely pays off a lot on the quality, because this will give you a much higher quality going forward. If you look then on top of that to the power consumption of the networks, then on the left side you have 120%, 120 watts. In the middle one you have 72 watts, while on the right side you have 56 watts. So you can see that the right side with distributed gain, it's not only that you have a much higher quality, but also your OPEX will be reduced a lot because your power consumption will be much lower. That is because we only have to use mimics. We only need a 20 dB gain amplifier in this case to overcome the cable loss. And that's the idea of this distributed gain architecture. So this is the way how we believe is a step forward, and it don't have to go from one to the other, but you can see that with normal amplifiers and a booster amplifier, you have a very good start to roll off, to go to that higher frequencies, a good use of it. And in the future, we can use the same booster amplifiers, but then a little bit more, we go to distributed gain architecture. And if you would do the calculations to go to 3 gigahertz, you would see that the right side, in fact, is the only option to do. If you want to go to 3 gigahertz, there is no way that you can drive enough levels out of amplifiers. So then the left side is completely out of the question. That will never work. The middle side will work, but it will suffer on the 3 gigahertz, while the right side can do 3 gigahertz signals even. So if you look to this, can we do extended spectrum DOCSIS with this? Yes, we believe we can. If we have a different technology like distributed gain, for instance, or booster amplifier with normal amplifiers, you will see that this is feasible. But if I look to then to FDX and FTTX, then I have to look to the booster more closely. Because what we have here is an example of an amplifier, and this amplifier, in fact, is an amplifier that has no dieback filters. So all the traffic that comes down gets gained down, and all the traffic that comes up gets gained up. So even when it is full duplex, even when it is 100 megahertz in both directions, it doesn't matter for such a device because we have no dieback filters. And this is a 20 dB gain amplifier, and it's only a 6-watt device. And now you see the big difference in the power consumption because I get 20 dB for only 6 watts. So if I have 2 of those in my network, I still have my 40 dB, while it's only 12 watts, and it is gain in both directions. That's the beauty of this product. So the upstream will already go to 684, and the downstream will already go to 1.8. And that, of course, gives you a huge benefit on that part. Here you have a small plot, how that will look like, and here you can see the black line, that is the downstream, and you can see that the downstream already go to 1.8 gigahertz, and is an anti-coax line. That means the higher frequency, the higher the gain. And of course, that's needed because you need, of course, in this case, to overcome the cable loss. And you can see now this will absorb the cable loss because the cable will have the higher the frequency, the higher the loss, while here we have the higher the frequency, the higher the gain. And you can see the blue line, and the blue line is the upstream. And so, as we said, we have now about 9 dB gain on the upstream, and we have about 20 dB gain on the downstream. So we have gain now in both directions, and we don't use filters. That means that it doesn't matter where you put the split. It doesn't matter if you even glue them together. You don't have to have a guard band anymore because you have no filters. And then, so in fact, what you are building, if you have only those small amplifiers, is one big pipe. So you have a transparent pipe from your RPD all the way to your CPE device. And what you do in the middle is a decision between the RPD and the CPE, because your network is one big transparent pipe. In this, because you have no filters anymore. So this can also help you to do FDD and FDX. Yeah? So that's of course is the beauty of it. And because we can do all of that, this is also possible to have a combination of this. Because with those booster amplifiers, you can go to 1.8 gigahertz, but you also can do FDX because you have no filters anymore. And you don't have to go to N+0. And that, of course, is a huge money saver if you want to go for FDX. The last few slides is about the network options that we have. And we compare 3 networks. We compare the network like we have here with 480 homes passed, high gain, 48 dB gain, amplifiers, high power levels, etc. We look to this. Then we look to the one where we have the normal amplifiers. But you can see here we have a small booster amplifier in the line. And then the last one is we have only small amplifiers in the lines. So we remove all the big amplifiers and we only have small amplifiers. And I put those 3 next to each other. So if you have the high power amplifiers, the normal with the boosters and the distributed gain with only small amplifiers. And then we want to look to the cost of such a network. How much does it cost us to build, maintain, and power everything combined inside to have this, run this network? So we look to the TCO. And the TCO consists of the OPEX, where you have everything in there about installation, calculation, power consumption, etc. And we combine then the OPEX together with the CAPEX, and then we have the total composite power, the total cost of ownership. It's too much difficult. The total cost of ownership. So all the costs involved in a network, how to run this. And if I look to that, the total cost of ownership to run a network for 10 years. You see, this is what it will cost us to build and maintain a network on the high power amps. So to build it, and this is for a network of 480 homes passed. We have the same where we have the normal amplifiers with the booster amplifiers, and we have it also with the distributed gain, where we have only the small amplifiers, where you can see all the cost. And if you will divide that by the 480 homes passed, you will see that the left one costs you roughly $58. The middle one is $50, while the right one is $37. And you can see the big difference is not in the beginning, because the beginning you still have to install them, you have to calculate your networks, you have to replace your taps. So the cost is almost the same compared to the others. But what the big difference is your OPEX. Because you don't have to go back to make an upgrade. You don't have to change the IPEX filters. And your power consumption is much lower, and your MTBF will be much higher because those units don't even get warm. So that's why they have a very long lifetime. So if you then compare to those 3 numbers, how that looks like, and how much data can I put through those networks, then on the left side, you will see that I have to step back already in my modulation scheme to be able to deliver a signal to the homes. While in the middle one, I can do 4K QAM all the way up, while on the right one, I even can go to 8K QAM. So if you look at that, how much data can you put through here? That on the left side, I can put 7.8 gigabit per second to the homes. While here we have 9 gigabit and here we have 11 gigabit. So you can see that the big difference in this is that here we have a lower cost, but we have more data to sell. Because at the end, for us, our customers, the MSOs, they are selling megabits. So if you look to the right one, you have to invest less over 10 years, but you will get more out of it. And if you then look to this, so that's why we believe that here you can generate coins, here you can generate bills, but here you can generate them all. Because overall, you have less investment and you have more what you can get out of it. You can sell more megabits. So the conclusion is that, yeah, existing networks can deliver the goal of 10 gigabit. And there are multiple choices. And that's great. It's not even that we have choices after DOCSIS 3.1. We even have choices after the next choice. So after the next step, we have more choices. Yeah? And the beauty is with the coax is that you only have to do this when it is needed. You don't have to do it before it's time. And so that's why they say in the US, don't spend the time before it's time, because you can do it. You can upgrade your network on the moment you need to do it. And think about the bigger picture. We can help you to create more gigabits that you can sell to your customers, and that's for the lower TCO. And overall, then it goes both ways, because you can sell more, but you have to invest less. Thank you. So I hope I managed in time.
Well, not quite, Jan, though, but I have to say the bit rate at which you speak is impressive. I've looked through this thing in advance, and I really couldn't see how I could interrupt it before we got to the end. So thank you very much indeed, Jan. That was very interesting indeed.
Thank you.
Right, we will now move on to our next presentation. This is from Henning Kroll, Product Manager at AVM GmbH. And he's responsible for the cable DOCSIS product line. So now we're moving to the end of the line, which is just as interesting as all the stuff in between. He coordinates the hardware and software development for the cable DOCSIS product line and defines specifications and requirements. I hand you over to Henning.
Hello, everybody. Traditionally, we are here to remind you all that yes, it is about networks, but yes, it is also, there's another component there involved, and that is the CPE on the other side. So good afternoon, everybody. Thank you, Mike. Thank you, Carsten, for inviting us to this panel. We are glad to be here. And I started my big rect clock to not take too much time in my presentation. So usually, you know, we do the CPE part of things. Remind you that there's another element that is important here, and this is what I will do today as well. Now, we heard a lot about cable and fiber, not so much about DSL and all the mobile stuff today, but we heard about the high bandwidth connections that are present today, and there's a lot to do to connect the consumers' homes with all the devices that are present there today, now more than ever, to one of those lines, whether it be cable or fiber or LTE or whatever it is. And this is what we are going to be talking about today. Now, we heard a lot about improving the network, the next steps, the steps even after the next steps in implementing network connections for broadband connections. And we'd like to remind you that even today, a lot of DOCSIS mechanisms or a lot of DOCSIS features are still on the table. At least the situation we have in our core markets, most of the DOCSIS features aren't even used yet, so there's a lot to gain with the existing features. We do have, you know, switchable duplexers that support more bandwidth or different spectrums, which are not even used yet. And there's a lot to gain in those perspectives there. And, you know, usually it's just investing in new CPEs that could help doing that, because as we see a lot of older DOCSIS 3.0 devices still being actively used in the networks today that prevent network operators from actually switching to newer features because they still have the legacy devices in their networks. Just a quick reminder on the DOCSIS side. So today's homes are getting more and more complex, and everybody that spent a lot of time at home this year, probably because of you know, the pandemic that's going on, knows that there are a lot of devices connected at home. The broadband connections that you are using at home is now more important than ever. And especially if you spend a lot of time at home, moving to different parts of your flats or into your garden, at least, or into my garage, for example, that was very important to me this year. I have to have a good coverage, and that's where all you know, more complicated scenarios on the end customer side comes in as well. So the consumer has a lot more devices connected through more complex scenarios at home now more than ever in meshed scenarios with repeaters and other devices, power line adapters, providing network connectivity to the consumer's home. So it's more complicated than it's ever been, and the devices, you know, are more elaborate than they ever have. You can actually now talk to them or gesture, do stuff like that to connect to your home. So this is all going more complex. We do have a new generation of Wi-Fi knocking on the door, being deployed at this very minute. We do have Wi-Fi 6 or 802.11ax, which is being deployed at the moment. So every roughly 5 or 6 years, we do have a new Wi-Fi generation. And this time it's actually optimized for dense or more denser environments. It's not about, you know, more speed anymore. It's more for being more efficient in more complicated environments. Of course, speed is also very important. We have to, you know, transport more data as well. But we have to do that efficiently on low latencies, and there has to be faster than ever. And of course, it may not use any power at all if possible. So low power consumption is very big, very important character or role as well in Wi-Fi 6 and this new type of Wi-Fi generation. So as we saw before, it's getting more complicated. Even consumers don't even know how many devices they actually connected to their network. I mean, if you add, you know, you have another Amazon Prime Day or whatever, and you add another Alexa-enabled device to your home, and you know, you just put it there and it sits there. You don't even really use it anymore, and you just forget it. And that's why we try to inform the customer about the network topology as well as possible, including all the intermediate steps in between, like repeaters, power line adapters, bridges, switches, etc., so that you actually know what you're using at home and you can manage that from a central place. And especially for network operators or telcos or MSOs, it's very important as well to help the customer out if there is a problem, to, you know, diagnose bottlenecks, etc. And one way of doing that, for example, would be to gather all the information that is available at the central access point at the device that is connecting your home to the network, and to actually get the meshed overview, and the connected devices can actually be transported via industry standards like TR69 or USP, can be displayed remotely. So you can, as an MSO or telco operator that has a connection to the customer device, you can use TR69 or USP to connect to the CPE, get the information, which device is connected where, at which or what speed. And you can have a look at the scenario. And if a customer complains that, for example, the speed test always fails or is slower than advertised, it usually isn't a big problem to diagnose, okay, you're doing that with your 2017 Android phone that was available cheaply there, and this is connected via a power line adapter via 2 other steps to the CPE. Maybe this could be a bottleneck. This can all be diagnosed with an overview of the customer's network. So not only the network itself, it's getting more complicated, more efficient, and more populated as well with more devices. Also the end customer's network is getting a bit more complicated nowadays, I guess. One big advantage of the newer available chipsets on Wi-Fi and additionally on Ethernet as well is that we are actually able to deliver more than a gig in the customer's home. This is on the left side, you see actual speed test data that we got from a colleague of us on a Vodafone consumer gigabit connection, which is usually, which is advertised as being 1 gig, which is usually over provisioned, so it's a bit faster than that. And with the modern interfaces like Wi-Fi 6 or 2.5 gigabit per second N-based Ethernet connection, you can actually have the gigabit that is advertised and more than that, as you see in the download connections here. The lower one is slightly above a gigabit and the other one as well. On the right side, you'll see the technical possibilities that are open to us. This was at an Excentis interop event early last year, 2019. Remember the days when we, were allowed to travel somewhere. And there you can see the downstream rate in a very early stage of the device using a couple of Ethernet connections was more than 4 gigabits. So all of that is available today on DOCSIS 3.1 connection or type of connections at the consumer's home. So just to give you a rough idea. This is all very important because simply it is good for competition. You can show that you actually deliver the gigabit and slightly more than that. It's not only 950 or 60 or whatever the usual speed is you get when you have a normal gigabit connection. You don't have bottlenecks anymore. It is a new speed generation, and especially the NBASE-T 2.5 gigabit Ethernet connection. That is something new. We checked that yesterday again to make sure it really is 10 years ago. But for us, it's 10 years that you have a normal 4-port gigabit switch on your CPE. That was totally normal, and this is the first time that something changed in that direction. So the Ethernet part was pretty conservative regarding speeds and changes. And of course, on the Wi-Fi part, we do have some evolution. We had the 802.11n, we had AC, we had 802.11ax, so Wi-Fi 6 now. We have some change there, and the device is slowly catching up to the access points to make use of the new technologies as well. But on the Ethernet side, a very conservative approach. So the biggest challenge that we are facing with all the new devices is that to get that into the market, there's a lot of stuff that has to be considered in software and hardware. So getting out a new device, an integrated access device, is more than just the Ethernet port and a bit of Wi-Fi, and that's it. There's a lot to be considered. There are software SDKs that are delivered by industry partners. There's smart home, there are software features, there are hardware features, there are changes in default settings even. If you change from WPA2 to WPA3, for example, that's a big step, a step we actually couldn't take this year because there are too many legacy clients that don't really support connections to WPA3 enabled access points. And all of this has to be brought to the consumer to make it happen, to make it work. And this kind of a challenge in a very complex environment with different clients, different operators with their needs and test scenarios, etc. So one of the things that we do is that if we introduce new features into the market, we usually do public betas. Public betas are something that has been around for years and decades even in software. It's pretty normal, but it hasn't really been available or that broadly used in CPE development or in telco integrated access devices. So that's kind of a different approach. And with those public available Fritz Lab or public betas, we introduce new features, ask the consumer to actually give us feedback about feature integration, if something goes wrong, if they like it, if they have tips for integration. And usually this is how it works. We create the arrow in the middle. We create the first betas, see if the platform is stable. If it's stable enough, we test it in-house. So our colleagues are usually the first one who have to suffer through beta versions. We let it run for a couple of days or a couple of weeks until the software is stable enough. And then we try to put that into a public beta. So we offer to consumers downloadable firmware with the benefit of being the first one to actually being able to use that, and the benefits of having to actually influence the development of certain features on the CPE as well. So they get the chance to have their voice or have their say in the development of software or hardware feature that we deploy in our CPEs. Now, this is not something that is very exciting, except for cable and PON operators who have very close eye on their networks. Usually, have a more conservative approach to that. So this is something that we started to do on our retail cable devices as well. So it started initially on DSL. And then we also did that on our retail cable devices as well. And this year was the first year that we actually did that together with an industry partner on the network operator side in the cable market. So we actually had a cable operator deploying the initial firmware. And we had a couple of hundred testers that we supplied with public beta firmwares to see if the firmware or the software changes actually work fine in that operator's network as well. So that was something new. If we got feedback like, there's a problem in telephony, or I don't know, a Wi-Fi client doesn't connect if you enable WPA3, then this was reported back to us. We checked the problem, fixed the issue, deployed the first version in-house, then put that publicly as a public beta as well. So we did a couple of cycles, and in the midst of a pandemic, this wasn't very easy, because deploying a public beta to people that actually rely on their software to work, that wasn't too easy. But we didn't lose any of our testers. That was very good. So we deployed that, and a couple of to be honest, month later, we were then able to release software that was the next generation of operating system for that particular device. So this is just an open call to anyone saying that using the customer, or asking the customer to actually provide feedback. There's always a group that likes to do that, has too much time on their hands, is interested in technical developments. Could be a good idea. In this case, it was very good. We had very nice feedbacks from customers from the field, and of course, a very nice press as well for that project. And this is what it looks like, AVMDE/Fritz Lab. This is where new features are introduced. So this was just my 15 minutes on don't be afraid to use the power of the internet to make your devices and your networks better on the CPE side. Thank you very much.
Thank you, Henrik. Nice and succinct, almost exactly on time. Thank you. Right, now we come to our final presentation. Our final presentation is given by Robert Pagano, the Visit Development Sales for Trimble. Now, this is a slightly unusual subject, which is no more or less value than Ellie does but proceed, but it is well worth listening to. Robert, the floor is yours. Your microphone is closed, Robert. He cannot hear you, Robert.
Robert, please double check.
Now we have you. No, that we have that was cast. Robert, we still can't hear you. We still can't hear you, Robert, I'm afraid.
Robert, you are here in our tool online, and please unmute your laptop in a dashboard. Well, Mike, should we start with a short discussion? And if Robert is able to make his presentation, then we switch over to the presentation. Mike, does it help? So that we can have a quick Q&A session for the first questions we have already here. Can we do it?
Yeah. I think we must, while Robert sorts himself out, please. So would you have any questions that come back from session number 2?
Yeah, we have a good question. What are the requirements for N+X to implement ESD? That's maybe a good question to Jan that you have.
Yeah. Jan, can you pick this one up?
Yes. You can hear me? Can you hear me okay? Yeah, okay, great.
We hear you fine. That's it, well done, we have you.
Okay, great. Now, there is not really a rule. We do think that probably N+6 is too much to go to for ESD, but N+3 in our calculation seems to work. If we go for the normal amplifiers with the boosters, we can go to N+3 in our calculations. So we looked into several scenarios, especially when you have the shorter ones, the N+1, N+2, it's easier, but N+3 is still feasible if you go for that solution with the 40 dB gain amplifier and the booster in combination.
Okay, here we go.
Yep. Robert, I think we have your voice.
Yeah, sorry about that. Some kind of funny. It did something funny. Right, so I'm going to have to go even faster now, Mike. So if you want to have me, here we go.
You're going to pop your camera up as well. Oh, right, that's it. We have you now.
All right. So,
okay, Robert,
thanks again. Apologize that to all the attendees. There was something funny in the audio. Trimble may or may not be a household word to this community. Trimble is a 40-year-old company that's been involved in what is referred to position, navigation, and timing for a little over 40 years. The company's headquarters is in Sunnyvale, California, but we've got about 40 facilities around the world. We're involved in quite a number of different vertical markets, essentially providing services that are always related to what is called the Global Navigation Satellite System, or I guess the modern version of not the modern version, but the full version of all the satellite constellations, example being GPS or Galileo. I represent the Time and Frequency Division, and the division has its roots going back to probably the original GSM days, when timing was needed to time the GSM network. We make subsystems and pieces that we sell to other manufacturers, and we also make timing systems. So I'm going to go quite fast in this. I apologize if I leave anybody in the dust, but I want to try and get these concepts across. So my goal today was to try and impart some learning about both timing and mobile backhaul and how that's evolved. from a timing standpoint, there's really three types of timing. There's an absolute timing or a timestamp. That's the easiest one for people to conceptualize. What time is it here in Italy versus what time is it in San Francisco, right? And being able to kind of get those aligned. Those are used in quite a number of systems. Frequency timing is kind of what makes the communications world go around because receivers have to be sort of tuned to the frequency of transmission coming from the transmitter. So it's about transmitting and looking for those pulses in a digital world at the same frequency. So it's akin to a Far West movie where the barn's on fire and the whole town folk are out by the pond passing buckets. The most efficient transfer of those buckets occurs when the person looks to his left, gets the bucket, passes it just to the right while she's just grabbing it just in time. If somebody is not paying attention, a bucket drops and transmission is impaired. Phase timing, which is down at the bottom, and I hope you can see this kind of silly analogy, has to do with lining up the leading edges of the pulses because 5G is going to be based on time division multiplexing. And as many of you know, radio channels tend to be set up with guard bands. So what happens is, you know, if these time slots don't align correctly in time, the 5G radios are going to have issues with spectral efficiency, which is eventually going to affect the throughput capacity of the system. I don't plan to talk about all of this. This is just to give you an idea that there are various number of clocks. The most basic clock concept has to do with the words master and slave, which in the modern world are probably less politically correct or less desirable, but it has to do with server-client relationship where the server tends to be the clock that has the highest accuracy, and in parts its accuracy down to the client clocks downstream. The grandmaster clock, which you may or may have not heard of, tends to sit, you know, at the higher part of the network and is a grandmaster which tends to never, let's say, you know, act as a slave. You can have slave-only clocks, okay, and you can have clocks that can be masters or slaves depending on what type of clock they are, okay. An example here is this mechanism called the best master clock algorithm, which essentially identifies a clock within a network that should be the master based on everything else that's going around in the network, okay? A lot of the equipment vendors build what they call boundary clocks into their equipment. A boundary clock essentially is a clock that can take clock from a higher order clock or a higher accuracy clock upstream and can then distribute that clock downstream. So it can act as a master and a slave in that scenario. You have transparent clocks, which basically try to adjust for jitter, okay, and look at the timestamps coming in and out of the device. You have one-step clocks, two-step clocks, and you have unicast and multicast, which I haven't put on here as well. So there's a number of clocking options. Those who are involved in synchronization know what these are. They may be a little bit foreign to some of the others who aren't involved in this. So those are the timing concepts. Let's talk a little bit about, you know, anyhaul as was first mentioned by Armin in his presentation. It once was called backhaul in the GSM days, and it was related to getting the signals from a base station, a radio, into the core network and traversing the access and aggregation network to get there. So some of these terms may be familiar to you, some of them may not. In the GSM network, You had the tower, which was referred to as the base station, or the BTS, going to a base station controller, which went into the network. And UMTS, those became the node B and the ring node controllers. Okay. The concept of front haul was introduced with LTE Advanced, whereby, and I'll show pictures of this shortly, whereby the actual radio was separated from the baseband unit that provides the electronic signals into the network, okay? And those radio heads can be remotely placed from a baseband location, and it's the baseband unit that then sends the signals back into the core and essentially becomes the backhaul. So now with a concept called C-RAN or Cloud RAN or centralized RAN, you have a separation between the radio and the baseband unit, and the connection between the baseband unit and the radio is the front haul, and the connection between the baseband unit and the network is the back haul. And now there's a mid-haul as 5G new radios are being introduced. The E node B in the LTE network becomes a G node B or 5G radio. And you have some of the functionality now being divided up, and those connections create a front haul, mid haul, and back haul. This becomes kind of interesting for the cable operator because now there's a number of places where a cable operator's network can be employed to provide parts of the transport to a mobile operator. Ducking back now here back into cable operator network, I'm sure many of you know, especially if you're a cable operator, that DOCSIS 3.1 introduced the concept of a standalone standard, IEEE 1588 Grandmaster clock in the network, which would provide timing to both the CMTS and the remote PHY devices. And the remote PHY devices then employ a DOCSIS timing protocol to provide timing to the cable modems, okay? And there'll be some, let's say, timing news in 2021 to support phase sync over DOCSIS, which is going to be critical to support any kind of mobile backhaul application for sure. I won't go through this in any great detail. This just kind of gives you a visual representation of PTP or IEEE 1588. It's basically a packet messaging protocol, and the idea is that you have messages which go between the master and the slave clock, and what's happening is there are calculations then made by the slave to try and isolate what its time offset should be based on timestamps being sent by master clock down to it, and then with the response, and then responses coming back. And it assumes asymmetry, it assumes symmetry in the network, right? So PTP, this type of PTP can get, let's say, a little bit tripped up if you take the classic fiber optic ring architecture where you're getting timing from the node that's next door, but suddenly there's a fiber switch, and all of a sudden you're going all the way around to the other side of the country through 27 nodes. The PTP protocol will be tripped up by that, okay? There are profiles. These profiles, if I go back to that, are a mechanism by which the message traffic is both defined and the messages are sent. The G.8561 or 65.1 protocol is a frequency time protocol. So that is used to provide frequency synchronization and provided the basis for all PTP synchronization through the beginnings of LTE. As it became clear that phase was going to become an issue, and part of the challenge with phase is the fact that the 5G telephones will begin to connect to as many base stations as it can find in the mobile network, not just one as it does today. A phase synchronization method was also required, and 82.75 is that standard. There are two of them. The 75.1 standard essentially is utilized when a network goes completely phase synchronous by employing boundary clocks in all of the network elements and utilizes a transmission technology called synchronous Ethernet and puts all of that technology everywhere, okay? And most of the telephone companies wish to move in that direction because the idea is that they would like synchronization to be like the power socket in the wall, right? You just plug it in and go. You don't have to think about engineering it. As it stands, as it's evolved over time, synchronization has always had to be engineered into the network. 82.75.2 is a method by which, let's say, you can have partial full synchronization, and whereby you don't have necessarily synchronous Ethernet and boundary clocks everywhere in the network, okay? And I think that might be kind of typical of what you might see in a DOCSIS network, by the way. This is in the package that you can download. This just simply provides kind of a picture of how these messages traverse. I won't go through this, but essentially you have a grandmaster at the top of the network getting its time source from a GPS antenna, and through the message exchange, it is synchronizing both boundary clocks and ordinary clocks and transparent clocks down the line in a network. This picture here, which is also in the package, kind of describes the famous 1.5 microsecond time alignment error between base stations. This was developed by the 3GPP to align both frequency and phase in the LTE Advanced network as well as the 5G network. And this kind of gives you kind of a picture, essentially, you know, you're trying to engineer your network to 1.1 microseconds with a little bit of buffer over here. The important thing to note is that as 5G really comes into play, some of the timing requirements between specific elements get quite, you know, accurate as compared to what the GSM network might have required, you know, 20 years ago. 130 nanoseconds, 40 nanoseconds, okay? So one of the things that becomes kind of clear, and I mentioned this earlier, is that the DOCSIS operator has an opportunity because of in the areas where the cable TV operator has extensive network, and that ubiquity allows, you know, both coax and fiber cables to be, you know, going down streets, going down neighborhoods, going into buildings, right? That gives the operator some opportunity to lease out some of that network to the mobile operator to place small cells, because the push is going to be, right, you know, in a true 5G, you know, Internet of Things world, we're going to be living inside of radio tunnels, and everything and anything that can be sensed, touched, spoken to, queried for data will be in there, and is going to require quite a bit of access. The other interesting thing is the coax network provides an opportunity to send power down the line to provide power to small cells, and you know, could enable kind of fast deployment. So to talk about this really quickly here, you know, it started with the baseband and the RF unit being at the top of the tower, right, in the GSM world. And then eventually that got broken up, where the baseband unit was separated, still in the same, let's say, cell tower, but separated from the RF unit, which was up at the top of the tower, and the baseband unit at the bottom. C-RAN introduced this notion of taking the baseband units and putting them in a separate place and connecting them with an interface called CPRI, which is a fiber optic connection to the radio heads. As we move into 5G, what's happened is that TDM connection becomes Ethernet, okay? And now you have the ability to have the baseband unit either at the radio or in a completely different location. They refer to them as baseband pools, okay, or baseband suites, okay. This is kind of an overall picture. This comes directly from the 3GPP, and you see kind of points where synchronization has to be provided here. This is a little bit my overlay. The DUs, which are distributed units. So now what's happened is that baseband unit intelligence now gets kind of split between the DU and the CU, and the DUs have to have synchronization in some kind of way, all right? And again, this is a picture going back to the way the world was. This may be familiar, right? It all started out with T1s, E1s, SDH, SONET. That's how backhaul first started, and synchronization was transported over that. And now what you have is you have this world here. So this is probably the most important picture here, and we'll stop. You see that the backhaul was originally going from the core network out to the radios, but now it's kind of going from, in the 5G world, from the centralized unit to the core. You have mid-haul going between the distributed units and the CUs, and you have the front haul, okay? These are right off of the ORAN site. ORAN describes kind of how synchronization and how they actually all should hang together. And I think I'll leave it at that.
Well, Robert, I have to say thank you very much indeed. If we were in a hall full of people, I'd get you a standing ovation for that.
Thanks.
Carsten, I think it's time we had a look at what questions we have.
Yeah, absolutely. Thank you, Mike, for moderating this session. Thank you to all panelists for the real good presentations we had. And we had a bunch of information got here in our ANGA COM Special online. We have as an urgent session for your panel the requirement from cable operators for DOCSIS 3.0 or DOCSIS 3.1 or DOCSIS 4.0 for a minimum standard for cable modem manufacturers to support. I think it's a good question we can discuss with Henning.
Thank you, Carsten, for the question. Well, I think all of us can agree that once something is deployed, it's very hard to get rid of. So I guess DOCSIS 3.0 is the minimum that we have to have. We tried when we entered the market using with DOCSIS devices, we kind of didn't do SNMP, we didn't do, or a very basic version of that. We didn't do packet cable provisioning for voice, all of that, and tried to convince the operators, well, ZIP is the answer, and use a TL69 server for doing that. So we actually, that was actually pretty hurtful for a lot of cable guys, to make use of DSL technologies. And it didn't work for us as well, because there's always a customer saying, well, they have to have that, otherwise we can't deploy that. So I guess for quite some time, especially, look at the German market, there's some, it's not pure DOCSIS 2.1 that's being deployed. There's a lot of leftovers because of backward compatibility to older devices that are still in the field. So I guess for quite some time, the minimum requirement will be DOCSIS 3.0 at least. DOCSIS 3.1, I think, has a lot of features up on its sleeve that will, at least in the bandwidth that we require currently in Germany, where a gigabit is more than enough, most of people say, because of, lacking of IPTV and all that stuff. So I guess that for quite a long time, DOCSIS 3.0 and DOCSIS 3.1 will do the trick, at least here.
Well, thank you. That's great. And I think Mike and myself, we are very interested. What is the result of our poll we had at the beginning? Well, yeah, that's an important question. Yeah, people waiting for it. Well, there you see on your screen the answer to our question. Well, FTTH has 64% and DOCSIS has 35%. I think that's a good starting point for our discussion we will have. Well, I've got here from the chat the question where we have a potential 5G small cells everywhere. And the question is, does DOCSIS 4.0 have the required speed and latency to be used for backhaul, fronthaul, or midhaul in this area? I think maybe Friedemann, are you able to answer this question?
Yeah. Okay. This question is a very interesting question. Of course, with so many small cells appearing, the idea is, can we connect small cells by the coaxial network and use DOCSIS 4.0 to connect it and to serve small cells? The answer of this question is not a white and black answer. I would say DOCSIS 4.0 is on the way to serve small cells. For example, regarding speed, 1.8 gigahertz in theory is possible to serve 20 gigabit. So in terms of speed, yes, cable networks are on the way. In terms of latency, I would say we have also paved the way by low latency DOCSIS and by mechanisms like remote MACPHY. I think there's a bunch of work to do regarding synchronization. Especially fronthaul has very aggressive requirements regarding synchronization. And I guess DOCSIS is a part away from that. So, but there are still or already ideas to solve that and to fix that.
Thank you for your answer. Mike, do you have any additional points for your panelists?
No, I think it's been pretty comprehensive one way or another. I have a residual question which I've asked quite frequently at various meetings, which relates to the extended bandwidth operations in the RF domain, in that an awful lot is spoken about the characterization of active devices and so forth, but very little is spoken about the characterization of the cables that the signals are being carried on. And the point I have here is that the majority of the legacy coaxial cable which is out there from many of the manufacturers is generally characterized as only up to 1 gigahertz in terms of its performance. And we are discussing taking the cable well beyond that. Now, that is not in principle a problem, because most coaxials will operate quite happily up to 3 gigahertz and beyond. But their stability of their return loss characteristics is something which is important to micro reflections and the like. And I haven't come across anybody who's actually addressed that problem, other than assuming that the software protocols will somehow manage it. Now, I'm not sure who I would direct that to. Perhaps it might be for Jan.
This question.
Yeah, I would love to answer that, Mike. Thanks. Yeah, no, we did a lot of research on this, also on the coax cables, because it's a good question. And maybe also to refer to the previous question where you said, can we do small cells, etc., over coax? We also use a different protocol than DOCSIS on the coax. For instance, what we can also have a different protocol that we communicate on the coax on a higher frequencies, let's say above 2 gigahertz, and then you can connect even up to 10 gigabit of data, connect the small cells over it with the latency in microseconds. So that is all feasible. So you don't have to be DOCSIS if we go to that area. We do multiple customers where we serve data over coax instead of using DOCSIS, but just on the network itself, not to the homes, but on the networks itself, to have an additional pipe there. And there we go even to 4 gigahertz. And that's why we did a lot of research on that part. And yes, we see there are different cables, like for instance, semi-airspace or things like that. They can have strange notches in the network or in the cable. But normally we see a very good performance. And that's why we even up to 4 gigahertz can at the moment communicate an additional 10 gigabits on the same coax. So yeah, and if you do the upstream, we did a lot of research on the upstream, because we all talk about, we go on the downstream from 1.8 to 1 to 1.2 to 1.8, but at the end it's only half an octave extra. If you see on the upstream, we go from 65 to maybe even up to 684. You see, it's a much bigger jump to go for the upstream than on the downstream. And to overcome that, that's why we did the calculations to see how can we do this without driving modems completely in saturation, that we have to deliver such a high level to be able to reach the RPD device. And that's why, for instance, distributed gain can help you, because there you have a small amplifier, it's much deeper in the network, and therefore you can still drive 684 megahertz on the upstream. So that is, I do believe it's feasible, but it's absolutely a very good question. That it is not a walk in the park just to say, okay, if the downstream works, upstream will work as well, because that definitely is not true.
Well, I love your answer. It's really hard to answer the question, Mike. It was a really good point. We got here from the chat the question: what protocols are used other than DOCSIS over coax cables? Well, it's hard to answer. Mike, you know who can be the one who can answer it?
I'm not sure. There are other protocols which you find on coaxial systems. I mean, there are the variations on the home plug type specifications, which use Ethernet over coax, which is an entirely difficult protocol and is a simplex type of operation. They tend to be proprietary, though. I think beyond the standards, I'm not sure I can think offhand, unless anyone wants to volunteer to throw anything else into the ring on this.
We do use a different protocol, as I said, on the different data pipe. And in fact, we use the protocol that's also used on the telcos, where they have built this data link between wireless substations. So that is, in fact, that protocol we also use on the coax is a single QAM carrier that we put on the higher frequencies to communicate to the small cells. So there are different protocols, but I'm not aware of different protocols from the network to the home. But inside the network, there are definitely more options.
Yeah, that's a good question. I have here one hand rising up. We will open the mic for Matthias. Can you ask your question? Mike? Matthias Gruber, can you ask your question? Okay, maybe he has some issues with his mic. Well, allow me a last question for Armin. Well, there is the question: what is the percentage of fiber ports operating with 25 GPON today?
Of 25G rolled out, you mean?
Yeah, rolled out. Yeah.
To be honest, it's almost zero, because for the time being, it's in a POC, proof of concept status. So we have quite some trials operating right now. But from beginning of next year on, I think we will start already the first qualification with customers.
Okay, yeah, it's a good point. Well, it's a point that we are on the edge of technology right here. Yeah, we are front runners with this technology. Yeah. Maybe Dave.
Maybe one last word of that. For the moment, it's in fact XGS-PON that is more or less the front runner for the next gen PON. And because it's a modular system, so you can migrate to 25G. Yeah, you are already prepared for the future. while for maybe for the time being 25G is not seen as the most important technology immediately. Yeah.
Yeah. Maybe Dave, do you have a comment on this topic? Because you also had a look on the 25G point.
Yeah, I can only reiterate what Armin said. I mean, you know, from a 25 gig perspective, there's two schools of thought. I mean, is it a direct path to, or do you go direct to TWDM type PON technologies with NG-PON2? 25 gig doesn't, you know, give you that quantum leap from 10 gig symmetrical to 25 gig. Maybe there's a case to answer there, but ultimately the market will tell us what to do.
Yeah.
Mike, do you have any comment before we come to an end of the session?
No, I've thoroughly enjoyed this session, and I thank all the presenters who've contributed to it, and I thank you, Carsten, for the opportunity to be part of it.
Yeah, well, that's a good point. I thank you all the panelists, my co-moderator Mike from SCTE, and I thank also to the audience. Well, at this time we have around 300 people running with us. That's a good number after 3 hours running such a hard job. Thank you so much for your good presentations, and where we will go further ways here with the online special. But the most focus is the ANGA COM next year in Cologne, where we have the chance again to see us face to face and to have a good discussion face to face. That is really helpful. And well, I thank you so much for joining us today, and I wish you all the best. Take care and stay healthy. Well, enjoy your time. Thank you so much.
Same to all.
Thank you, guys.
Bye bye.
Thank you
Thanks
for
for listening.